The common gate amplifier consists of grounding the gate and applying the signal to the source. It's convenient to use the T model when studying the common gate configuration, because when we do, it puts in series the signal with its source resistance in series with the resistance seen looking into the source. So this 1 over G sub m and the R signal resistance, the internal resistance of the signal, are then in series with each other. In this analysis, we're going to ignore the early effect, and thus R0 has been omitted from our analysis here. R0 again is the resistance, that the early effect resistance that would be connecting from the drain to the source, and it significantly complicates the analysis. And once again, it has minimal effect, and so the neglecting of it doesn't minimize the results that we'll get. Our first observation is that because the source, the signal, is connected in series with the source, the voltage actually applied to the source here is going to be reduced from the signal, from the signal voltage by a voltage divider between these two resistances. The gate has been grounded, and so we have then that Vin is equal to V sig times this resistance here, 1 over G sub m divided by R sig plus 1 over G sub m. From observation, we also recognize then that this term 1 over G sub m is the input resistance. The input seen looking into the source when the gate is grounded, Rin then is simply 1 over G sub m. Now while we're at it, this is probably a good place to just remind ourselves of what G sub m is. G sub m, you'll recall, is equal to K sub n prime W over L times the overdrive voltage VGS minus VT. So it turns out that G sub m is a relatively large value, and 1 over G sub m, the input resistance, is relatively small. This is a real drawback for this amplifier configuration, and frankly it limits its usefulness in discrete device amplifiers. But it turns out that it has some very nice frequency response characteristics that make it useful in IC designs. So even though we're not going to get into IC design in this class, we study this common gate amplifier as one of the 3 common configurations that does find applications beyond what we're going to see in this class. We can determine the open circuit gain AV0, which is V out over V in with no load resistance connected, by realizing that V out is just negative. V out is negative I times R sub D. Now the current I is referenced going from the gate to the source, so we can write then that the current going from the source to the gate, which would be negative I, is equal to just the voltage here would be in, divided by 1 over G sub m, the resistance, or negative I is equal to V in times G sub m. Combining those two expressions, or replacing negative I with V in times G sub m, then we get V out is equal to V in times G sub m times R sub D. And the open loop gain, or the open circuit gain, AV0, then is just V out divided by V in, or G sub m times R sub D. The output resistance, R out, is found by deactivating the source, which then of course again makes this dependent source 0, and the resistance seen looking from the output back in is just R sub D. So we've got then that R out equals R sub D. If we now attach the load resistor, once again R sub L is in parallel with R sub D, and we can now calculate the closed circuit gain A sub V, Well, it's going to be the same thing as the open circuit gain, only we now have R sub L in parallel with R sub D. So A sub V then is equal to G sub M times R sub D in parallel with R sub L. We can calculate the overall gain G, which is equal to V out over V sig with the load resistance connected, by writing the expression for V out. V out is equal to V in G sub M. V out is equal to G sub M times the parallel combination. Now we've got the load resistor connected times R sub D in parallel with R sub L times V in. We saw up here that V in is a subdivided portion of V sig, so replacing V in with this up here, with this expression there, we get then that V out is equal to V sig times 1 over G sub M over R sig plus 1 over G sub M. That's just the V in term there, times the G sub M times R sub D in parallel with R sub L. We get then G by dividing both sides of this equation by V sig and going through and multiplying this G sub M term. We get that G, the overall gain of this amplifier, is R sub D in parallel with R sub L divided by R sig plus 1 over G sub M. This is kind of a mess. Let's just go back and recap it then. We found that R in for the common gate resistor is 1 over G sub M and is relatively small. We found that R out was equal to R sub D and relatively large. We found that the open loop or the open circuit gain was just G sub M times R sub D. We found that the closed circuit gain just brought R sub L in parallel with R sub D, so we ended up with the closed circuit gain being G sub M R D in parallel with R sub L. And then we found that the overall gain, G, was given by this formula here.